Hey, good morning, everyone. So, this is the day third. I hope everybody has same energy that you have on first day. Today, you guys did a good job. Most of them answered correctly whatever the questions were given to you guys. So that's good. At least some of you have a very good knowledge about basic optical microscopy, SVM, and VM. But some of them is still lacking that one. So today we will discuss about very basic thing, very standard about optical microscopy, scanning electron microscopy, transmission electron microscopy, and then scanning thermal microscopy, and we will have some about Raman spectroscopy. Because when we talk about this 2D material or 1D material, so Raman spectroscopy is also pretty relevant. So still some participants are working on the quiz. So you have 5 more minutes. So in previous lecture we discussed about nanomaterial and we have a sense about the size. Means when we are talking about this 0-dimensional, 1-dimensional, and 2D material. So today we will discuss about really means how we can visualize them. And here is a simple kind of like scale. So where you can see means what we can see with naked eye with simple optical microscopy or with electron microscopy. So with the eye, we can see up to 100 micrometer easily. So like for example, width of a finger, that lie around like 1 centimeter. And then with light microscopy, we can see up to 200 nanometer easily. And then beyond that, we use this electron microscopy. So with electron microscopy, we can see even one individual atom. So today we will discuss about optical microscopy. I will not spend much time on optical microscopy because it's very standard. So just I will go very quick on optical microscopy. But then we will discuss about scanning electron microscopy and EM, and then scanning thermic microscopy, and some discussion about atomic force microscopy, and finally some discussion about Raman spectroscopy. So the very first one is, what is microscopy? So microscopy is the technique of using microscope to observe objects at, like a very small one that we cannot see with naked eyes. And microscopy has widely used for all of the application related to material science, even for chemistry, biology. When we talk about like this confocal microscopy, so that's very specific for biological application. Nanotechnology like SEM and TM, they are very unique for nanomaterial. Even STM, like for example, you go up to atomic scale. They have a wide application in medicine and in other different fields too. So first about optical microscopy. So in optical microscopy we use visible light. And the first design was developed early in 17th century. The resolution limit is 200 nanometer, and it's very common, like for daily application. And even you can have that optical microscopy in your lab if you are studying in high school or in intermediate. So that's very basic one. But the question is here, why do we have a resolution limit 200 nanometer with a standard optical microscopy? Anybody want to comment on that one? The question is, why do we have resolution limit of 200 nanometer for standard optical microscopy? Anybody can answer my question?
So visible light spectrum we can see around from 400 to 700 only. Beyond that we cannot see. Though we have whatever resolution.
What is the 400 to 700?
That visible spectrum.
Visible spectrum, yeah.
Beyond that you can't see with our naked eye. That is the reason. Oh.
Good. So the optical microscopy that magnifies an object in two steps. The first step, to place the object between the single and double focal point, that results in a magnified image in a real time. Then you have a second lens that is used to pick up this image exactly in its front focal point and then generate a higher resolution image of that object. Now the question I do have for you guys, you have the statement here. Can you draw that on your picture? That, like it is. Read the statement and draw a picture on a paper. Can you do that, please? Can you share the paper with them? Just try to make a picture for a standard optical microscopy based on this statement. Use your pen and paper, please. So here it looks like that. You see on the screen, you have these two lenses. So the object, it will go through the first lens, and then you have imaginary image there, and then you will use the second lens to magnify that one, and then you will have this magnified a virtual image. That's how it looks like. The question that I asked you previously, why do we have a resolution limit of 200 nanometer? That's based on Earth's theory. So according to this theory, the resolution will be equal to 0.612 lambda divided by NAL, where DRS, that is resolution, lambda is wavelength of the light, and NAL is the numerical aperture of the lens. And here, normally we consider wavelength of 550 nanometer, as he mentioned, like visible light is 400 to 700 nanometer. So if you consider 550 nanometer, so the answer will be 200 nanometer. So that's why for a standard optical microscopy, the maximum resolution you can get, that will be around 200 nanometer. Beyond that, you cannot see clearly. What about numerical aperture? So that is a like a unitless value, and here it's equal to beta 1 sine theta, and it will be same for both if you have different media. So for example, in first case, the angle here, this is a theta 1, and here in second one, this angle is theta 2. But in all cases, NA will be same, theta 1 sine theta 1, and second one, theta sine theta 2. So it's called a Snell's law. Aperture. So you use camera, and in camera, if you see, they have a particular aperture limit, and aperture that you focus on the object in a different way. So here you can see clearly, if you have a large aperture, so simply half of this picture is clearly visible or focused, but if you have a smaller one, then you have like a more clear picture. So for simple optical microscopy, what are the key components? So the first is definitely eyepiece, that is your outer lens. Here you can see on the picture on the top, and then you have objective turret. So here we connect these objective lens. Number 3 is objective lenses, and then you have focus knobs. So this focus knob is to do it up and down to properly focus on object. And then you have stage to hold your sample, and then you have light source too, and then you have a mechanical space. This is a little bit relatively advanced one compared to very standard one, because here we have this light source on the bottom, but for normal one we don't need a light source here. Optical microscopy can be divided in different ways. The first is, for example, bright field microscopy. So here we use direct illumination, and it's very common in biology, but it has low contrast for unstained sample. Then we have dark field microscopy. So it enhances the contrast in unstained sample, and here we use the oblique light. So there is a one term that is called oblique light. Anybody have any idea what is oblique light? It should be very simple for person who has done master in physics or undergrad in physics. Oblique light. There is a one term, oblique light. Anybody want to comment? Can you please share?
Not perpendicularly falling.
What is that?
Not normally falling on the surface. That is not normal in film.
That's not a very clear one. In a simple word, oblique light is light that passes through the edges of the lens, not at the center or not in the, that's like a straight plane of the lens. Then we have next one, phase contrast microscopy. So that's pretty unique. If this is not a standard one, here we use the difference in the phase of the light to get the image. So that's more clear here. It's provide like a very clear image due to the phase shift, and it's very useful for live cells and no staining required here. Then we have differential interface contrast. So here we use the polarized light, and it is able to produce 3D images, and it also provides very high contrast image without staining. Then we have fluorescence microscopy. So here we use fluorescent dyes or proteins, and due to excitation and emission wavelength of the light for these fluorescence, we can create the image. And this is very common in biomedical research. Now I do have a question here for you guys. The resolution of optical microscopy is 200 nanometer. Can we make that one using fluorescence or not? And if we can make that one, how we can do? You can use the mic, please. Anybody? Go ahead. Are you feeling shy? Yeah, please provide the mic.
Sir, I don't know exactly.
It's not your chance, okay? What is there?
Maybe we think by adding fluorescent dyes, some fluorescent material to components and sample of specimen.
Do you guys understand? Can you simplify that one?
That is by to the sample by adding these specimens, like for the specimens by adding these fluorescent dyes, so that you get amplification by amplifying.
You can amplify that one, all right? Any explanation? Yeah, go ahead.
Sir, I don't know exactly, but I think I'm right. In the fluorochrome, we apply the UV light and it absorbs the UV with the shorter wavelength and emit the visible light in the longer wavelength. So we are working within the, we are applying the UV light in that. So I think we can get more magnified image. Due to the fluorochrome, we get the visible light from that. But we are applying blue color UV light, we get the visible light.
But there is another very simple approach here people have used to get a nanoscale resolution. So they do multiple imaging on one cell. So for example, you have a different type of these fluorescent, and that will be excited for one wavelength and another in second wavelength. So they do multiple imaging, and then they impose those imaging on top of each other, and then they are able to get the resolution at nanoscale. Then we have this confocal microscopy. So here, in place of normal light, we use laser light, and here we have the higher resolution, that's simple conventional fluorescence microscopy, and here we also can get a 3D image. So this was very standard technique that we can use for material characterization. But again, most of the technology that whatever we discuss here, for nanomaterial, they cannot provide a resolution at nanoscale. They can provide resolution for biomaterial at nanoscale using like fluorescence or confocal microscopy. But for normal material, we cannot get resolution at nanoscale. Here is the one technology that is called light-seek fluorescence microscopy, LSFM. As I mentioned here, we use laser excitation source, and it emits a Gaussian laser beam into the system to focus onto the sample. So simply we have this laser source here, and then we have this laser beam, and then this will go to the beam expander, and finally passing through the cylinder lenses and illumination objective, it will hit the sample. The beauty of this technology is that it's not hitting the sample from the top or all over the sample. It's hitting the sample from the side. So minimum exposure to the laser light. And here we can adjust the position using the scanning mirror of the laser beam, and we can determine where it contact the samples. So you can select which area you want to image. And then we have third beam expander. So it will increase beam diameter before it reaches the cylinder lens, and it will allow for a tighter focus in the narrow dimension of the light sheet. We have cylinder lens, so the application of cylinder lens is to focus the beam in one dimension, so that a thin light sheet is formed at the sample after the beam passes through the illumination objective. And then we have illumination objective. It's placed perpendicular to the detector, and it determines the FOV. There is a one term FOV. What is that? Field of view. And again here, it will depend on your aperture value, the quality of your final image. Sample mounting is standard, so here you want to put the sample, but it's very important for these samples. So, because we want to pass the beam to the side, so it's very important this sample mounting. It should be very perfect actually. Here is a kind of like comparison between fluorescence microscopy and laser sheet fluorescence microscopy. So here in first case you can see that this light is coming from top to bottom, right? But here it's passing from left to right. And here you can see the direction of illumination and direction of detection. So here, illumination is left to right and detection is top to bottom here. But here in this case, it's just, it's in same and opposite direction here. So due to this LSFM, we have we expose a very smaller volume of the cell in comparison to the conventional fluorescence technique, and it will reduce the phototoxicity and avoid to damage your sample. And when it comes to the imaging, you can see clearly the difference, how beautiful image you can get with LSFM compared to the standard confocal microscopy. So on your right hand side, here, this is from the LSFM and this is your conventional. So it looks like very clear and provide the image of a cell without any damage. So that's very useful for your this biomedical application or biological application. And these LSFM have a resolution that's in micrometer, and sample size can be larger than centimeter, and it's like a relatively less expensive, but and photo bleaching is also very less. There is one new work that recently published. So here, to modify the aperture of this light sheet microscopy, in place of water, in place of gas or air, they use the water. So this is air coupled scarf and this is a water coupled one. And when we replace air with the water, so capture angle is increased 2 times. And due to the increase in capture angle, we have a better image related. So that was very basic about optical microscopy. Any question about optical microscopy? If you want to talk or you want to discuss. Good, thank you. No question. It means you guys are not getting if what I'm talking, huh? So the second is about scanning electron microscopy. So this is, to me, like even I did master in physical chemistry, I was not able to see a scanning electron microscopy, how it looked like like in real world. So SEM, that is a type of electron microscopy, create very high resolution image, and here we use electron beam that provides image. And the first SEM was developed by Max Knoll in 1935, and then in market it came in 1965. So that was a little bit about your SEM here. This is how SEM look like. So first you have here on the source, so that's your electron source, and then you will have aperture, then condenser lens, and then you will have a second aperture and second condenser lens, and then you will have here a coil that is called stigmator and deflection coil, and then you will have final lens and final aperture, and then you will have your sample. So electron gun that will produce the electron beam, and the condenser lens that will direct the beam across the sample, and the detector that will capture emitted secondary electron to make the image. In this case, we need a vacuum, and we will talk about why really we do need vacuum, why we cannot do it in a normal condition. But before we go to that part, first we should know about how we create an image. So when electrons interact with the surface of the sample, they produce signals in the form of secondary electron, backscattered electron, and X-ray. These secondary electrons, they are used for imaging the surface here. And these backscattered electrons, they actually for compositional analysis, and X-ray that is generated, that's for elemental analysis. So using SEM, you will have a couple of things. You can have a morphology of your sample, and even you can have elemental analysis of your sample. That is called EDS. So what is secondary electron here? And what are these backscattered electron? So this figure makes you clear what is your secondary electron, backscattered electron, and X-ray. So in first case, when electron beam hit the atom on an electron, transfer the energy, and then secondary electron are emitted. And this is inelastic scattering, and that is due to like a collision between these two electrons. The second, and these secondary electrons, they are used for topography. They create a topography of your sample. Then to have the material contrast, we use backscattering electron, and in this case, these primary electrons simply they will go through the atoms and come back in the same way. No collision happened there. No interaction with other electrons. In third, we have these X-rays. So whenever we hit the electron hit any atom, so it can create another electron plus some X-rays. So the question was, why do we need vacuum? Why we cannot do it in a normal way? So if we don't have vacuum, so it will be very hard to control the like a flow of these electrons or to focus the electron, and definitely we will have problem with chemical and thermal stability and of the filament, because under standard condition the filament will burn and we will not have electrons anymore. And the second is the signal electrons, they must travel from the sample to the detector. So here pressure of the chamber is very important. If you have any like air there, so those electrons can hit the air and you have an artifact image there. So that's why we have a vacuum for this scanning electron microscopy and even transmission electron microscopy. Sample preparation, it's a very straightforward. The first part, water must be removed. The second is sample must be trimmed to an appropriate size, because here, depending on the setup, you can have sample from like 1 centimeter square to 1 centimeter square, but not maybe wider than that. The third, if you have metal, so it's just straightforward, there is no need to do any extra preparation. But non-metal sample, they should cover with a conductive metal. And the reason is that we should cover with conductive metal, because if you don't cover with conductive metal, then electron inflection will not happen. So that's why we need to have that one. So here are some advantages and disadvantages of this SEM. So first is like high resolution images, but again it's a relative word when we talk about high resolution. This is high resolution in comparison to optical microscopy. A superior level of magnification, again it's relative to optical microscopy. But here we have a large depth of field, and we use electromagnets as an alternative of the lenses. So here we don't have a real lenses, we use these electromagnets in place of these lenses. And 3D data of the sample can be measured, and preparation of the sample is relatively simple. Again, one word, relatively simple. So here relative to TM, relative to STM, not relative to optical microscopy. But here are some disadvantages. Like first is, for example, it's relatively costly comparison to optical microscopy and hard to maintain. And sample have to be built in the vacuum. And if we have a non-conductive materials, then we need coating of the conductive material. And then it's very sensitive to the vibration and external magnetic field, because external magnetic field, they can deviate the direction of the emitted secondary electron. And then you have issue with your images. And then these SEM, they generate radiation. So you should have a safety plan for that. Any question about scanning electron microscopy? So here are some samples, very standard sample that we, like a showing the application of SEM image. Like the last one, that is about calcium oxalate dihydrate. Here, these are pictures. They are like a cold kidney stone. Then we have this SE image of the photoresist layer. So you can see the number of layers here. And then in first case, for example, you have normal circulating human blood cells. So this is very standard. You have this one. Next is transmission electron microscopy. So, like SEM, transmission electron microscopy, we use electron gun. But here in place of secondary electron or backscattering electron, these TM transmit electron through the sample, and when it transmits electron through the sample, we can create a high resolution image. The big difference between SEM and TM, so the SEM scans the surface, only surface here, but the TM allows imaging of the material structure at atomic resolution. And this TM microscopy, where we have a beam of electron that is transmitted through a very thin sample, and TM provides a better resolution in comparison to SEM due to its transmission mode and ability to analyze the sample thickness. When I say sample thickness, so it should be at nanometer scale. The basic principle of TM, so it has an electron beam that will obviously generate the electrons. And then the second is sample interaction. So the electron beam passes through the sample, interacting with the atoms, and then finally image formation. So these transmitted electrons, they are focused onto a phosphor screen or a detector to create an image. So here simply you can see this picture. So we have this electron beam, and here you are sample, and this electron will be transmitted through the sample, and then here you have the image here at the bottom. The basic component of your TM, obviously you should have electron gun, then conventional lens to focus the electron beam onto the sample, same thing like SCM. Same way we have a sample stage and we have objective lens to focus transmitted electron into an image, and then we have projector lens to magnify that image before it reaches to the detector, and then we have the detector. So these are the very basic components of your scanning electron microscopy. And here we are using magnetic lenses in place of your standard glass lenses. A little bit more about this TM image processing. So higher energy electrons, they will penetrate distance of several micron into a solid, and if these transmitted electrons would be focused, so they can create one image there, but it's focusing of these electrons that's very important to have your final image. The processing, so first is sample preparation, how to prepare the sample. So you should have a thin sectioning. So if your sample is like in the form of film, so you need to cut them in a very thin form, less than 100 nanometer thick. If it is thicker than that, maybe electron cannot transmit through the sample, and it will be very hard to have the image. You should have chemical fixation. So especially about biological samples, so they are chemically fixed to preserve their structure, staining. So some sample may need staining with heavy metal to enhance the contract, especially biological sample. Then we have option of cryo-TM, especially for biological samples. So here we can simply, like in the form of cryogenic or in the form of frozen, we can scan those samples and have the DNA analysis. The advantage, obviously very high resolution, we can go at atomic scale. The second is internal structure imaging. So it's not on the surface, it's through the sample. So you will have internal structure imaging. And the third is detailed imaging. So it's capable of imaging nanoscale features, or like for example, various virus or nanoparticles or thin scale. So pretty kind of like broader application here. This is just one example showing you the TM of 1 nanoseed. So here we can see the atomic resolution of this material here. And this is widely used for all nanomaterial. The next technology that we will discuss, that is scanning tunneling microscopy. Yeah.
Do you have any idea regarding smaller, selective area X-ray diffraction? Diffraction or X-ray diffraction techniques using TEM. Selected area X-ray diffraction. As well as X-ray also. X-ray diffractions also. Two methods are there. Any ideas of this?
Yeah, it means like that will depend on the sample, right? For example, if we have a graphene and then we have that type of image, so simply you will see 6 different dots, providing the complete information that it's a hexagonal or not. Again, it depends on the material, but definitely you will have that one. TM has that capability to do that.
Thank you, sir.
So the next is your SPM, scanning tunneling microscopy. So that's pretty powerful technique for the surface analysis at atomic scale. And the principle is a little bit modified of atomic force microscopy. So here simply like atomic force microscopy, we have a tip, but here tip is operated with the potential, and it depends basically on the quantum tunneling. So quantum tunneling is the kind of like a phenomena where electron can transfer if you have a very tiny gap between two kind of like two objects. For example, a tip and the surface. So between tip and surface, electron can transfer if there is a very, very tiny gap. So that is a kind of like a tunneling or quantum tunneling. And it can provide you real space images of surface topography, and it can be used for, like to understand electronic properties of your surface. Again, whoever designed this one, Craig, Winning, and Andrews, so they got Nobel Prize for this discovery in 1986. So in terms of like key component, so you will have one scanning tape, and then you will have piezoelectric controller scanner to control your, like a tip. And then you will have distance controller and scanning unit. You will have vibration isolation system because it's need really very, like a vibration free space. If there are tiny vibration, you cannot do that one. You cannot run SDM. So you will have a very specific space for this one. You need to work with in ultra high vacuum chamber because it's very sensitive to environment. You cannot do that one in normal environment. And basically here the tape will move near the surface, and then you will apply the voltage. So due to voltage difference between the surface and tape, a tunneling effect will happen, and tunneling current will pass through that one, and based on that one, you can report the movement and display the moving, scan the surface by the tape. So by that process, you can have a very atomic scale image, even even at single atomic, even subatomic scale, you can get with SDM. So there are two different modes. One is constant current mode. The second is constant height mode. The word is defined like a constant current mode. So simply here you maintain a constant tunneling current when you sweep the tape on the sample. In second case, you keep the constant height when you scan the sample. In first case, the tip's vertical movement that is recorded to create a topographic image, and that is used for imaging surface topography. But in second case, you simply use variation in the tunneling current or record it to create an image, and it is very useful to understand the electronic property of your sample. So these are the two standard modes for SDM operation. And here are some examples about SDM samples or SDM characterization. The one is in 1989 with IBM scientists. They simply position 35 xenon atoms on nickel surface using SDM, and they characterize that one. Actually, they wrote this word, IBM, using atom. The second is showing blue platinum tip surface of the platinum, and the third is that is 7 nanometer to 7 nanometer single zigzag chain of carbon atom on GAAS surface in blue. So simply here you can see these carbon atoms on GAS. So that's the capability of your scanning tunneling microscopy. Any question about scanning tunneling microscopy? It's kind of like a modified version of atomic force microscopy. The way you do atomic force microscopy analysis, same way here you do, but in place of piezoelectric force, here we use the voltage to control the heat flow.
Sir, can you compare the resolution of these three?
Why that?
Resolutions.
The resolution, as I mentioned, is at subatomic scale. For the SDM, you can have a resolution at atomic scale. You can scan atom by atom.
Millimeter, sir?
What is?
SEM and TEM.
It's I'm talking about SDM. SDM and TM also can provide at atomic scale, but SDM cannot go. SDM maybe can go up to, if it is very, very advanced one, it can go up to 10 nanometer, for example. If it is normal one, so it will be very hard to have a very good image of 10 nanometer object with the SDM. like we have a tabletop SCM. So those they cannot provide any resolution below, like for example 20 nanometer or 50 nanometer.
So STEM can provide a more resolution.
What is that? Gian has higher resolution compared to SCM. And STM has the atomic scale, the highest one. Again, means the difference between TM and STM, it's not about resolution, it's about what one understands. With STM, you can understand a lot of things like electronic property of those atoms. But with TM, it may be difficult to do that one. But for TM, you will have a big sample, you can characterize relatively simply. But STM, it's still relatively hard to operate when you have this atomic resolution. Yes.
Thanks.
Cantilever is a conductive or non-conductive cantilever in STM.
In STM, it's as I mentioned, the fundamental mechanism of the STM is quantum tunneling between tip and surface. So that should happen there. So in non-conductive case, it cannot happen. It should be conductive.
What about the sample preparation for STM?
For STM,
Is the sample preparation the same as 10 or 7?
for STM, like there is no need very specific sample preparation if it is a conductive or it's a metal. But if it is non-conductive, then maybe you do some coating to make it a little bit conductive, so you can have it on like in person. Otherwise, for STM, it's straightforward. It's very easy to have bigger sample. For example, you have a nanopowder, right? So simply take tiny nanopowder, put on silicon substrate, and then you are ready to go. But again, you have to be careful because in both cases, in SCM and TM, we have the high vacuum, so those powder forms should not fly in the channel. They should stick to the surface. Yeah.
It was kind of same or time, generally, as per my knowledge, carbon tape will be used to stick the sample, especially nanopowder sample.
Yeah, you did, yeah.
Yeah. In that case, how do we neglect or that silicon or carbon compositions will be obtained in the image, elemental composition. So how do we decrease that, or how do we eliminate that portion? Is there any other sampling model technique rather than using the carbon tape?
When we use this, like a case, for example, that we're talking about double carbon tape, right? So you will have a very high signal for the carbon there. But in place of that one, you can use like a copper tape. Still, you will have a very high signal for the copper, but relatively low compared to the carbon because it's heavier than that one. So yeah, but it still means we need that one. We cannot avoid that. In EES analysis, still you will have that, and some percentage of your oxygen and carbon from line one. So that's how they say.
Thank you.
Any another question? Good. So next one is atomic force microscopy. So I have played a lot with atomic force microscopy because during my PhD, I did a lot of work on carbon nanotube. So we don't have TM, we don't have SCM there in the lab, but we do have AFM. So I played a lot with AFM. So the basic idea of AFM was developed in 1986 by Winning and Gerber. They invented AFM. It provides very high resolution image. And when I say high resolution image, even you are able to image a single wall carbon nanotube. And the diameter of single wall carbon nanotube is just around like 2 to 3 nanometers. So you can do that one with atomic force microscope. And it depends, again, it depends on the instrument, and it depends on many factors there. Like, for example, tip. What type of tip you are using in AFM? If it is very sharp enough, then you can have a high resolution image. If it is not really very sharp enough, you cannot have very high resolution image here. The basic concept for AFM, so the AFM raster that will scan a sharp probe over the surface, a sample, and measure the change in force between the probe tip and the sample. So here we are measuring the force difference between your tip and your sample. And it can be operated in both, and it's useful both conductive and non-conductive material, and it can also provide 3D topographic images. And in addition to that, the AFM have different modes, like for example, conductive AFM. You can determine the conductivity of your nanomaterial, whatever you have on the substrate. So the principle of AFM, so as I mentioned, we should have some piezoelectric forces. So the physical parameter probe, that is a force resulting from difference interaction. So AFM image is generated by recording the force change as the probe is scanned in the x and y direction. And here sample is mounted on piezoelectric scanner. So it makes sure that you have three-dimensional positioning with high resolution. And the force is monitored by attaching the probe to a V-level, cantilever, and that is a tip there. So here in the picture you can see the laser that's hit the tip here, and then it go back to the detector. And the variation in this intensity of this laser, depending on the force between tip and the surface, you create an image there. So there are three modes here. One is contact mode. The second is tapping mode. The third is non-contact mode. So in first case, when we have the contact mode, so tip is always in contact with the surface. Here like that, number one. And this type of like condition or the mode is helpful if your sample is very hot, and you can have that one. The second is tapping mode. So here cantilever or the tip that oscillates and tap the surface, and it reduces the lateral forces and sample damage. So in this case, you are not damaging your surface. You keep your surface, like it's pretty good. And it's ideal, very ideal for the soft material, and it's measure the oscillation amplitude. Third one, non-contact mode. So in this case also, tip oscillates above the surface, and it will measure one-on-one forces, minimize sample damage, but it's difficult to implement in ambient condition. So these two first one, that's very common. Contact mode and the tapping mode. They are pretty common for your sample analysis. If you are expert and you know like a pretty good expert, then definitely you can go for part one too. And here this is the graph here that's telling you about force and distance curve. So depending on the force and sample distance, you can have like a tapping or non-contact or tapping mode here. This is a very simple AFM image, and here resolution is at micrometer scale. So simply I'm showing you this image to you guys. If you have an image, a high profile image, and simply you draw a line, so you can calculate how deep or how high the morphology you have on the sample. You can easily calculate that one. And as I mentioned that AFM is widely used for different applications or imaging, The first one, for example, on this is a carbon nanotube here, and on carbon nanotube, we have selectively deposited these particles. And here we can see that means how these particles, like the height of the particles is clearly visible. So clearly you can find out the size of those particles on carbon nanotube. The second is about the first sample here, that is silicon carbide. And on silicon carbide, you do the sublimation and then you grow the graphene. So simply here you can see the graphene on silicon carbide surface. And here this is your, like a relatively high. So because silicon carbide that have a stack structure. So that's why here you see these steps here and you see the height of these steps. But after graphene growth, there is no clear steps and you assumedly have multi-layer graphene. The third example here about conductive mode. So here you can see simply these kind of like tubular structure. But when you run the conductive mode, when you analyze this sample with conductive AFM, so simply you can see a current image here. So all these are the current profile, and here you can see current is in picometer. So these are conductive, and this is a non-conductive area. So not only these kind of like tubular shape conductive around them, they also have some conductive surface here. Like here we are studying the junction of carbon nanotube, because carbon nanotube, they have a very good interaction too, but it's not necessarily that that junction is pretty good, strong or pretty strong electrically. So here you can see that in first case, it's not very conductive here, but in this case, it's very conductive. It means the interaction between this carbon nanotube and this carbon nanotube is kind of like a physical contact. So here conductivity is much higher compared to this junction. So AFM is widely used to study such kind of like a conductive network, either in polymer nanocomposites or itself. Any question about atomic force microscopy? Yes, go ahead.
What type of cantilevers generally would you use, sir?
Generally you can use silicon-based cantilever.
What if it corrodes? Is it corrosive?
You need to replace that.
I have operated in a small university, but corrosion is taking place for that cantilever.
Yes.
What is the reason behind that corrosion?
So it again means like the interaction of this tip with the surface, right? The tip is very, very unique, very sharp in the bottom. So if you reduce the diameter of the tip by running the experiment in contact mode, then only one solution is there, you need to replace the tip.
And one more thing, sir.
Yeah.
Do you have done any nano limitation using the cantilevers for mechanical problems?
I have not done that personally, but definitely AFM is widely used for nano integration. And that can be done using the contact mode and using hard tape.
Yeah.
Yeah.
One more thing, sir. The domains, magnetic domains will also be observed. Is it true? Using AFM in the magnetic mode?
I'm not sure about that one.
Okay.
Yeah, I'm not sure about that one.
That's okay.
Yeah.
Sir, what kind of material we use to in the tip for checking the biological samples?
What is that?
For the tip material, usually for normal samples we are using silicon. For in biological samples, what kind of material? The tip is made for what kind of material?
You can use that one itself for biological sample too, but you can modify this tip in a different way. Like for example, even you can have a carbon nanotube on the tip. So on the tip, you can attach a single carbon nanotube, and that's very unique in diameter, very small in diameter, and that will give you very sharp resolution image.
That may affect the biological samples. Sir.
But again, for biological sample, you will not go for contact mode.
Okay, sir.
Yeah, you will go in non-contact mode.
Thank you, sir.
Yeah. Any other question, guys? Good. So we are done with most of these surface analysis or the morphology analysis of nanomaterial using optical microscopy, scanning, or transmission, or atomic force microscopy. Just a couple of slides to give you idea about Raman spectroscopy. So the Raman spectroscopy, that is a non-destructive technique, means you don't have direct physical contact with the sample, but it can provide you chemical and structural information. So here basically the fundamental concept behind is Raman effect. So here these waves, they will interact with the molecule, and depending on the vibration of the molecule, you can analyze the composition or the nature of your sample. So depending on the vibration mode of those molecules, and it creates a chemical map of the sample. So for example, if you have a graphene, and if you do the Raman mapping of the graphene, so simply you can get a map, and it will tell you that it's a pristine or it's a defective graphene. It's very unique for that type of material. As I mentioned here, we will use here kind of like a Raman effect to understand or to study the sample. So simply here, you can see if there is a wave with particular energy. So here may be three different modes for this energy, and it will pass the molecule. So you will have three different energy here, three different conditions. First is Rayleigh scattering. So here it will go from infrared absorption to the virtual energy state. Second is Stokes Raman scattering. So here it will go, like it, go from bottom to top, but then it will stop one step before. Then third one, it will start one step up and come down to the ground. So these are three different types of scattering. One is anti-Stokes Raman scattering. Lambda scatter is less than lambda laser here. The second is Rayleigh scattering, where lambda scatter is equal to lambda laser. And third is Stokes Raman scattering, where lambda scatter is higher than lambda laser. So this is one example of inelastic scattering that's used for imaging and chemical analysis of your sample. And here we use Raman shift, and that's typically expressed in the wave number. And here is the formula for the Raman shift. Delta, here is W in wavelength in centimeter inverse is equal to 1 by lambda 0 nm minus 1 by lambda 1 multiplied 10 to the power 7, that is called nm to cm conversion. And delta W, that is called Raman shift, and is expressed in the wave number. So simply using this formula, you can have information about the Raman shift. There are some examples. So first is about the same material, like you have diamond, silicon, or germanium. They have similar bonding, but different atoms. So having different atoms, but similar bonding, still you will have a different shape into the Raman field here. The second here, for graphene and graphite. So for pure graphene, you will have two very characteristic peaks. One is D band and the second is G band, and that is here written by G dash. And in graphite, if you have again two peaks, but the ratio of this peak to this peak is completely opposite. So in single graphene, you will have very high peak this one and a smaller peak second one. The third one, again, this is about similar material with different bonding. So on the top you have this diamond, and on the bottom you have the graphene. So here you have two different material, but with similar type of carbon-carbon bond. The third one, that is about similar material with different size. So if you have like a bulk or at nanoscale, still you can see a unique characteristic peak due to Raman Raleigh escarpment of the way. That's all for the day. Any question? Go ahead, use the mic, please.
So is it possible to identify the single layer graphene and bi-layer or more layers
With what?
with Raman spectrum?
Yes, it is.
Raman.
Yes, it is.
How?
With the Raman spectroscopy means the ratio of these two bands, D band and G band, that is sensitive to the number of layers on the substrate.
It doubles.
Yeah. Even if you have two layers, so then you will have the ratio will change. There is an article that's published, I think, in 2009 actually. They completely on this study, studying the single layer graphene, double layer graphene, and a multi-layer graphene using the Raman spectroscopy. You can have a very detailed theoretical analysis there because it's not a simple one.
So D over G should be doubles.
Is that?
D over G.
D should be higher for the single layer graphene.
D over G.
Yeah. And it's also, like when you have a defective graphene, then you have another peak here for the Raman system. And that will tell you that that peak is specific for defects in the graphene or carbon structure. With the ratio of D and that peak, you can determine or identify the purity of the graphene. That's also possible.
And the symmetry of the 2D peak actually, or over
Symmetry of the
2D
band. That's, I'm not sure about that. But I will recommend you read that article.
Yeah.
The very first article about identifying or differentiating single layer graphene, double layer graphene, and multi layer graphene, and even comparing single layer graphene with defective graphene. So you will have a very, very clear idea. Because it looks like simple here, but behind this one there is a lot of like a numerical formula, very complicated formula. Believe me, it's not very straightforward like SCN would here.
With the optical microscopy also, we can able to differentiate the monolayer and bilayer.
With simple optical microscopy, you are able to do that, especially for the graphene. But again, you have to be careful because the substrate very, very important there. If you put those graphene on like for example, on copper, you will not be able to differentiate. So the substrate play a very, very important role to differentiate single layer graphene, double layer graphene. And simply that can be done seeing the color of the graphene.
And the similar analogy, how do we just use this Raman spectroscopy for the single word nanotube or multi word nanotube?
Yeah, it can be used for that material.
You can easily differentiate.
Yeah,
Single
sure.
layer with the channel.
Yeah, it can be done.
Single word and the multi word.
Yes, both of them.
Thank you.
Hi, sir.
Yeah.
Sir, especially in STM and AFM, you are can use for electronic properties, right, sir? For analyzing electronic. Is there any modification available for spintronics using STM and AFM?
Yeah, means for the AFM definitely means you can modify, like a date, and you have freedom means to modify, like a overall setup, and then you can go for that one.
So using AFM and or STM, you can easily able to analyze for the spintronics applications.
Yes, you can. Yeah. That's already used for that one. For this one, but it's been from
Thank you.
But you have to do these extra modifications here, not a standard.
So the modification is in what kind of in the tip, or we have to
It's not only tip, if you need to modify the whole setup. For example, in ASM, if you need to create additional component that can sense or that can modify the electronic property of the material, and then you can analyze that. So, yeah. Yeah. It's very cool. Especially in like in US, we do have this national laboratory, so they have a huge freedom or huge money to modify the setup, all those things. So that we can use. But in normal case, it's very hard. Again, these whatever I discussed, they are very standard technique. I have not discussed means how we can modify this technology to have more information about the samples or to advance the characterization, like analysis. So simply we can have a lot of modifications. For example, Raman spectroscopy. That can be combined with optical microscopy itself or fluorescence spectroscopy itself. So then you have two-dimensional or two things simultaneously. So there are a lot of things. Like in Raman spectroscopy, one more example, that is called SERS, SERS Raman spectroscopy, right? So that will provide you a very unique, technology, and that will provide you for example, how molecules interact with the surface. Very unique one. We have done that one for to understand MnBF4 molecule. The MnBF4 molecule is a pretty big molecule, so that's an ionic liquid. How that ionic liquid interacts with the catalyst at different potential. So there's a lot of application for this. Especially maybe you need to do some integral analysis.
Good morning, sir. Sir, you have mentioned about the ionic compounds about the interaction you are studying, right? So what about the radiating molecules? So nowadays, so many, even the sensors are developed by radiation molecules, right? So how we can analyze those molecules' properties, structural properties that we have invented like that, so using these techniques?
No idea. My answer is here, no idea.
So
yeah, I cannot comment on that one. I don't know anything.
We can't do. So, is there any chance for doing the Raman spectroscopy and like that spectroscopy analysis for knowing about the wavelength or what wavelength what they are emitting like that, sir?
No, this technology will not provide that information. Yeah. Like neither AFM, neither STM, neither GM, these technology, they will not provide that information that you are looking for.
Okay, sir. Thank you,
Yeah.
sir.
So we have some break, and after break we will have again discussion here, and we will discuss in detail about whatever the question you guys have. Okay? So take a break. It's a 20-minute break. 20-minute break. Okay. Yeah.
Everyone please be seated. The session will start in 2 minutes. If anyone now, please call your colleagues or friends.
So before we go to lunch, we have 1 more hour to discuss about the application of this technology for sensing application. And here just we will have a discussion, and discussion will be based on our questions and queries and interest. So who wanna ask first question, or who wanna raise any points or any queries or anything about application of this technology for sensing? Otherwise, I will ask question. Yes, sir.
You please repeat the question, please. I didn't get that.
I have not asked any questions so far. So anybody want to have any thought? Means like, what is the use of? I love AFM, so I will ask for AFM. What is the use of AFM for sensing application? Means how will we can use AFM for the knowledge whatever we get from AFM for sensing application? Please give the mic here. Bless you.
Sir, AFM is just gives the topography of the sample.
So the question is how we can use for sensing application, right? So what is your take on that? No, can you talk? Yeah, so C means to know the conductivity of material. The question is, if we can measure the conductivity with simple electrometer, why do we need AFM?
If it is more conductive, as per the knowledge what you given. Actually, I am from biotechnology background. I don't know much more about all these things. And what I listened during your talk, the material which have the, two carbon nanotubes there, sir, when they have the more physical contact, they exhibit the more conductivity.
Yeah.
If they have the more conductivity, they will give the more resoluted image. Right? Like if the image is more clear, then it may have the more conductivity. If it have the more conductivity, it may have the more sensing ability.
That's a very interesting point here. Means like when we talk about sensing, so tunneling current or the quantum effect is a very kind of like interesting phenomena in sensing domain. And especially when we have, for example, carbon nanotube junction. So how these junctions are modified or tuned in the presence of analyte. That's a very interesting topic to study. But before going to the molecule, first you need to know without molecule how they are looking, right? So AFM is pretty good for that one, at least conductive AFM. I have done some work on that one. Like one of my experiences, we discuss carbon nanotube in anti-polymeric matrix. So when we discuss carbon nanotube in polymeric matrix, and you do simple AFM topography analysis. So what you will see? You will see that there is some tubular shape that is underneath very thin polymer film. But you will not know means are they making any conductive network or not? Are they part of conductive network or not? And if you use the conductive AFM, so simply you will have two separate images, one topographic, one conductive, and you can see which carbon nanotube is part of conductive network. Very easy. And you means you can see means when you interference of analyte, if polymer is swelling or the junction between carbon nanotube is broken. So simply with conductive AFM, you can see that one too. So that's very interesting for at least these sensing applications. And we have seen the application of Gian, how Gian can be used for sensing applications. Yeah, you have seen that one?
So actually, before and after sensing application, the surface and morphology can be analyzed using flame and same images. So how it affects the morphology of the material before and after sensing applications.
Yeah.
So we can study the morphology using the flame analysis.
Good. So can you explain a little bit means what they expect the change in the morphology after sensing application?
So actually, in electrochemical sensor, if one material we can take a similar shape or morphology. Morphology cannot fully affect it after the sensing application. Maybe it may be break or it may create some porous in that materials. So some of little bit changes only we can observe after sensing application, before and after.
Yeah, that may be possibility. And here means like in advanced technology basically. I'm not talking about any standard case. In advanced technology, especially for the TM, you can see these some analyte, how they interact with the atoms. You can see that one too. Just simply changing the environment. For example, if you put some oxygen, so you can see how oxygen interact with some metal catalyst here. At least in catalyst I know. And if it works for the catalyst, so definitely it can work for sensing application too. But that's a very kind of like a complicated experiment we do have. Any another thought about TM? And, yeah.
It's a silly question.
No. It's a discussion.
Yeah, but if we use any gas in ppms in the ultra high vacuum, are we able to do that? Can we?
That's an answer, right? In special case, it's not a standard TM. In standard TM, you cannot do that experiment. But with modification, I don't know actually in detail what they have modified, but we are able to understand like electrochemical reaction on the atomic catalyst by using the TM. Even they have some means like, for example, how CO2 molecule interact with the surface. So that's good. Yeah.
Sir, it's not, sir,
Yeah.
it's not about gem. I have one doubt related AFM, sir. You have mentioned that for sensing the biological, for taking the analysis of the biological molecules, the tip should be CNG like
No,
that.
no, that not should be that one. That's just, I provide one specific example. Means if you have a, a particular cake that can interact in a different way with the substrate.
So, is that activated CNT or activated carbon like these are we are using for that or
What?
normal?
The question that I will ask you, what do you mean by activating carbon in the tube?
Activator means it should be interacted with the molecules, like it should be able to capture what the molecules, the substrate and all.
Yeah, it should have means that's a fundamental, I would say, mechanism for sensing it, right?
Yes, sir.
And there are some example actually that AFM itself with the modified T has been used to analyze or to do the sensing. So AFM has been used. And here basically means just simply we need to modify the T. And modifying T itself is a very, very challenging task because you are playing at a very small scale. And how precisely you will do so, that's a challenging task. But if you have a very good facility and very good technology, so definitely you can do that.
Okay, sir, thank you.
So then, related to them, we are making currently we are using the copper mesh and like that metal like meshes for replacing the substrate, right? Like can we replace that with other glass-like substrates and all?
With other,
Glass-like
that
material.
substrate must be conductive here. But definitely means people have used in place of copper, they have used graphene mass itself. Yeah.
Why not graphite?
What is that?
Why not graphite? Why there?
Why not graphite?
Yeah.
That's a very interesting question. Anybody want to comment on that one? See, telling why are we not using graphite in place of graphene mass or graphene for the TM? I will ask you the first question before that. For the TM analysis, why we are using a mass? Why we are not using a kit? That's the first question.
I don't know, sir.
Anybody want to comment on that one too? Yes. Why are we using a copper mass or any mass structure for the TM analysis, for the TM sample preparation, in place of the thin film? Yeah, you can have mine, please.
First requirement for the sample should be very thin because the transmission of the electron pass through the sample. So it should be a thin. Otherwise, if it is a bulky, then we cannot have them.
Yeah. So that's the right explanation here. And that's why we use a mass structure. We have mass here, right? Copper mass or any mass structure. It has a lot of hole there. So simply you put the sample and then you scan that one. And when you talk about graphite, graphite is a pretty interesting material. Because in graphite, if you see the electrical properties or optical properties or thermal properties, you have to go down or from left to right. It's different. It's completely different, right? And if you use the bulk graphite, so definitely like you will not able to penetrate electron through the graphite. So you cannot use that one.
Thank you, sir.
So one more doubt.
Yes.
So you have mentioned that you have worked with single bond carbon nanotubes and multi bond carbon nanotubes.
Yeah.
can you just explain or can you give idea about that which one is better or
Like, I would say better in the sense, in which sense you want to ask?
glucose sensing?
Glucose sensing. So the first thing is about playing with multi-wall carbon nanotube and single-wall carbon nanotube. Working with MWCNT is very easy. Easily you can disperse them into the any like any, for example, acetone or alcohol. It's very easy to disperse them. The second, multi-wall carbon nanotube, they are always conductive. They are not semiconductor. Okay. Single wall carbon nanotube, depending on like they are zigzag or they are armchair. Depending on that, they may be semiconductor or they may be conductive. And it's very hard to work with single wall carbon nanotube in place of multi wall carbon nanotube. So if you see easy processing and make sure that it's conductive, so multi-wall carbon nanotube is pretty good. But then the question comes is, what is the advantage of single-wall carbon nanotube in comparison to MWCNT? So with SWCNT, if you are able to fabricate a device, it is much better than MWCNT. Because the semiconducting property itself is a pretty interesting for the sensing application. Because here, depending on electron donor or acceptor, you can change the quality level of that semiconducting material, and then you can see the signal. Yeah. Yes.
You said, if we change the cantilever in AFM, we are able to sense the gases that you said. So what kind of cantilever should be taken there?
It's I didn't say about gases, I think about biological molecules. Yeah. Then we have this, like AFM also has the capability to be performed in liquid. So if you can do, like if the cantilever will work as an electrode material, and then you have analyzed into the liquid, so when interaction will happen, you can see a corresponding change in, like for example, conductivity. So that's what I mean, and I was talking about that.
The very same cantilever generally uses silicon cantilever.
Yeah, silicon is the standard.
Is there any other cantilevers are available?
Yeah, even means what I mentioned is carbon nanotube on the top of that one. That's also available, but price is pretty expensive. Always that's it, like the price and the quality of the tip. Even if you see the size of the tip, if you go below 20 nanometer, you want to have a tip that's tip size is less than 20 nanometers. It at least means, I would say, 5 to 10 times higher than one. And means working with AFM, even when you just put the tip, so sometimes the simply break it. So that's it, that's a lot of money.
What is the if the AFM is working vacuum? Is there any accessory like if vacuum chamber is used for the same material? We do in ambient conditions like atmosphere chamber and we use vacuum chamber. Is there any morphology change?
I think morphology, we will not observe any change in the morphology. Again, you get again the like for example, morphology of what? If you want to see morphology of single crystal,
Yeah.
or like for example, right? So the tiny change in the on the surface, definitely you can see. Because if the diameter of the nanotube is like for example 2 nanometers, and simple is scanning, I'm talking about scanning on high profile. If there is like a 0.5 nanometer enhancement of thickness, so simply you will be able to see. But if at atomic scale, when there is like a sub nanometer, it's very hard. at some nanometer scale.
So one more thing, sir. We take the thin films, what are the thin films? The zinc oxide, whatever it is. What is the role of roughness using, I mean, measuring the roughness of the thin film using air thread? Is it giving the exact information about the roughness exactly?
It gives pretty nice information about roughness of the sample. Even you can simply you do the line profile. So simply how does your surface look like, and then you have like you have image on the side you will have a data table.
Yeah.
So in that data table you will have all like information for all samples rather than one line profile, and then you have clear idea how rough is your sample.
Even thickness of the thin film is also measured.
Thickness, it means you need to do the cross sectional level.
Okay, yeah.
Yeah, not on the topography. Yeah. Or maybe it takes some particular angle
Yes.
on one particular angle.
Why we need to maintain the PSP or photosensitive photodetector in the middle itself?
What?
While focusing the laser light onto the cantilever, a parameter that is photosensitive photon detector PSP has to be maintained in the middle. That is the initial condition to be met. Then only we will get the topography 3D image. So what if that PSPD is not maintained in the middle part?
If it is not there,
Means, shall we get any image or we don't get any image, clear image of that sample?
I think it's something like means if detector is enough capable to see the difference, how the light is coming back to that one. So if it's tiny, if tiny variation is happening here, if detector is capable to do that, then there is no need that one. And again, it's to enhance the magnification or enhance the quality of the image. More precise you want to have. Yeah. Any idea means if you guys have thought about, for example, Raman spectroscopy application for sensing. So means I have not seen any article so far. Maybe I can study that one, or if you guys have studied, or if you have any thought, Raman spectroscopy for gas sensing application. Have anybody seen that one? Most of you guys are interested for sensing, right? Good. Any idea about? Anybody want to share any thought or any recent discovery in the sensing field?
Give us some introduction about the chemoresistive sensor, introduction of generational sensors, so that it will be helpful in the afternoon session.
Can you elaborate a little bit more?
No, I want the introduction about the sensors. So that afternoon session, we are going to hands-on experience on the sensor navigation, right?
Okay, yeah.
So it will be helpful for us to get the generational sensors or types.
Tomorrow I will have 2 lectures. That's basically on sensing.
Okay.
Yeah, first lecture is about carbon nanotube and second is about graphene and for sensing. So tomorrow we will have.
Other principles, sir, they are
Yeah,
afternoon, we are going to have the hands-on experience on the sensor navigation, right?
Yeah, there is some sensor. You will have some sensing experience.
From that only.
Yeah,
Some
so-
introduction are the basic principles behind this.
So I think today we are going to do any class that means it's a gas sensing or it's a something. But I think they have funny nanofiber on the electrode, on the conducting electrode, right? So we want to see means how the conductivity of that material will change in presence of any analyte. And the simple analyte, what I'm assuming, Either we can use methanol vapor, simply, like put methanol in one vial, and you can simply hang your electrode on top of that one. And you can see how the methanol will change the conductivity of that one. And again, it depends. The mechanism will depend on the type of material that you are using for sensing. And it will also depend on what type of device do you have. So for example, when you have this polymer nanocomposite, right? So in polymer nanocomposite, simply it's swelling of polymer materials in presence of that analyte. And swelling in the sense, you have a, for example, carbon nanotube junction there, and with the tiny swelling of that polymer matrix, it will just change the gap to 0.1 nanometer. So that gap enhanced in 0.1 nanometer will change a lot in electrical conductivity. So that type of things we will see. And the second is about here, the token level. For example, you have a material A, and that material A you are using for sensing application. And then in presence of analyte, if material A is getting D dot or N dot, right? So depending on that one, you may see the positive signal and negative signal. So today activity that we have at 2 o'clock, that is designing hierarchical quantum resistive chemical sensor for detection. Again, as I mentioned, I think they are using polyaniline nanofiber, not carbon nanotube or graphene. And QMI means like the word. Quantum resistive is a very unique. Quantum resistive word should be used when you are using any material that has a quantum property. So in this case, I don't believe that funny will have a quantum effect here. But still you will see, if I will remove the quantum word, so you will have a resistive chemical sensor for something else. So that will happen.
Sir, if you change the chirality of the nanotubes,
Yes.
is there any enhancement in the gas sensing?
It's as I mentioned, it's this one, you say chirality, I say chirality. It's a tiny, but it's taking the basic property, the fundamental property of carbon nanotube from semiconducting to conducting, right? So then the sensing mechanism for semiconductor material is different, the sensing mechanism on conductive material. In semiconductor material, it's a change in the Fermi level due to interact with those analytes. If it is going to positive side or it is going to negative side. So that will define the sensing mechanism. But if it is pure conductive, then there are some, like, for example, hopping effect, tunneling effect, scattering effect, all those effects will play in the sensing mechanism. Even interaction between carbon nanotube to carbon nanotube, carbon nanotube to electrode itself. So there are different effects. So it will have a big effect. Yeah. Same thing here for the graphene means like if you have a graphene nanoseed and on graphene nanoseed, you put second graphene layer with one particular angle. So with just changing the angle of second graphene on top of one graphene, you are changing the property of material. And changing the fundamental property of any material will change the basic mechanism of your sensing mechanism. So that's always there. Anybody want to explain what is resistive chemical sensor, by the way? Yeah. It's a very simple definition, right? Yeah. So here in resistive chemical sensor, the resistivity will change of your sensor. But we can say in another word too, it's conductivity as well, right? Resistivity or conductivity that will change in presence of analyte. Another question maybe means like for resistive sensor, your sensor should be really very conductive, or it's okay to have its very high resistive. High conductivity. So in general, actually means if you have a higher resistivity, so you have higher sensitivity. In general, yeah. I'm not talking about a specific case, but in general, if you have a higher resistivity of your sensor, so then you have higher sensitivity. Because then you have more chances to break the conductive network, and that if you break the conductive network, you are enhancing significantly the resistivity. So that's why it's higher, and it's a ratio because it's. And you measure the sensitivity, so you are not just simply measuring the resistance or resistivity. It's a ratio between the difference in the resistivity and initial resistivity. So how that number will be higher, that we need to take. Good. Any more questions, guys? Yes, go ahead.
Sir, please tell us about the different sensing properties.
Keep that secret for the day.
David, not in the, you are please.
Yeah, repeat question one more time, please.
Tomorrow you are speaking about graphene, I think.
Yeah.
Other materials you can tell us today.
All the sensors, like it's a very, very basic science. Like if there is a semiconductor material, so it doesn't matter what type of material you do have, like it's a zinc or it's a carbon nanotube, it doesn't matter what semiconductor material you will have. Mostly you will have same type of sensing mechanism or same type of phenomena. So it just like a couple of things will change. The selectivity of the sensor that may change depending on the material, and the sensitivity of the sensor that may change depending on the material. And so these are the a couple of key things that can be different. Otherwise, the mechanism mostly will remain the same for all semiconductor materials. Because it's a fundamental science here. So sometimes we cannot break the fundamental science. Table is very silent today, by the way. You guys are talking yourself, man. You don't want to say anything with us? Give the mic to them, man.
Okay, sir. It will be last question after this.
Yeah, go ahead.
Sir, sorry, I am asking right or wrong, I don't know.
No, that's
Sir,
okay.
okay, sir. Sometimes in recent developments, we are sensing the brain signals and convert it into an interfacing, biointerfacing is happening today itself. We know recent developments are going on those things. What kind of, how the brain signals are converted into computational signals, and we understanding that what the brain thinking, like those things now we can able to understand in nowadays, sir. How does things happening? I want to know about this, sir. Because anyhow, we are sensing that what the brain, we are sensing by the signals only. No?
I'm telling you, it's currently what's happening. At least, if you read very recent article, not about fundamental science, about the science in technology. So machine learning or artificial intelligence is, just playing a very, very important role there. Even like they have, like recently I was reading one article, they are able to work with 200 analytes and with hundreds of the sensing devices together, and using this machine learning tool, they are able to differentiate different type of analytes and explore the sensing mechanism. So if you will read those type of articles, and you will see means how complicated are they if you don't have a background in machine learning, or if you don't have a background in those computational study. So they are look like very complex but very interesting to see.
It's interesting, but what I think is brain consists of millions of neurons, billions of neurons. But how they exactly find that these things brain want to convey now? How did they find those things? I'm confused with that, sir. I cannot exactly understand what's happening between this brain signals into our understanding. Confused with that.
That's a tough question to address. But here, like, can you repeat one more time your question to understand properly?
Sir, exactly with Tamil I will explain. Okay, sir. Exactly what the conversation happening between the computer and the brain. How we exactly find that what the brain want to say out. So recently Neuralink we are implanting some materials in the brain and we convert those things controlling the system with our only brain signals. How does the signals exactly find what we brain what want to say?
So for that first I will recommend you, we need to understand what is the brain, right? What's happening in the brain? How the neurons or electrons, how they are migrating, right?
Yes.
And it's a very complex system. Brain is a super complex system that acts. And in presence of, like if you are thinking anything, so how those neurons or electrons or those channels, how they are changing. So depending on that one, simply means we could have some, like output for that. And here, I will say like in MIT one team, one of the team, they are trying to make a very small antenna to implant into the mind, into the head. And then the antenna can transmit the signal. And outside you can record those signals. So depending on the activity of mind, you will see that either intensity of the signal or the way the signal is.
Intensity.
Yeah. So those type of work is going on. It's having those type of like transistor or these transmitters into putting those them into the mind, and to understand in detail what's happening there.
Thank you, sir.
So, I think new concept are like in a kind of latest concept, but they're using Raman spectroscopy in protein structures and like coding and everything by understanding the vibrational modes of some protein structures are like amino acids. So can you explain that if you have some idea about it? Like using Raman spectroscopy to understand protein structures by understanding their vibrational modes.
Raman spectroscopy, yeah, for Raman spectroscopy, it's very straightforward. Depending on like how the vibrational energy will change there, so they can design the molecule. And again, with Raman spectroscopy, it's not just only one point. You can have million points to get a 3D image of that structure. And if you are able to get a 3D mapping of any compound for the structure, then definitely you can figure it out, the chemical structure and the physical structure of that.
So basically used by pharmaceutical companies or someone who's making targeted drug delivery, make the protein very active.
Can you repeat one more time?
So like I'm saying that Raman spectroscopy can be used by pharmaceutical companies who are making proteins. And like, kind of if there are some any mistakes, if you want to improve the quality of the protein, they can also use to understand what is going on.
So before that means like when product will come, so this will have means a complete analysis. And again means like it can be very difficult to have 100% a purity of the production of that type of molecule. Yeah, still there may be some chances like 99.9% for example. But it's not only on one technology, means you cannot rely only on one technology to just study or to check, means it's pure or it's accurate or not. It should be a combination of the technology.
I'm not asking the questions.
Yeah.
I would like to answer the question what the boy asked you earlier. I think it may be the maybe not. I mean, it's not the correct, but it may be right. What you are asking earlier.
I am asking that how does the brain signal exactly converted into a computational process? How do you know that? That's my doubt. Brain is a
What is
biological
the
system.
interface that transfers the brain signals into the
Computation. It is a
computation?
biological system. How converted into computer with exactly? That's the main question. How it's properly working. I want to know how it's working.
Actually, two things are there, up to my knowledge. One is the artificial intelligence. It is the interface which directly converts the signals from the brain into the computational thing. And the interface is the thing which detects the electrical signals or the chemical signals. Actually, in between the neurons, there may be the transmission of signals in two ways. One is the electrical impulse, and second one is the chemical impulse. If they sense the electrical impulse or the chemical impulse, these signals or a chemical signals can convert into the transmitters. Okay. With that, the interface, with the help of some artificial intelligence, it may say this now the person goes to elevate one thing. His brain wants to elevate the thing. His condition may be elevated, and he may think very depressively. Like that, based on the signals, some sensors sense the signals, and that signals transmitted to the interface, and that interface converts the signals into the what you are observing in the computer lab.
Yeah, that's okay. But what I thought is, even for understanding that, we need a great, much more amount of. Sorry, we want a permanent data already fixed, and then only we can collect,
Yeah.
extract from that. We need
Up
a
to
data
my knowledge,
reference.
any interface or any computational tool, it doesn't tell the what our brain exactly going to do, exactly going to think. Not exactly going to think. If now my situation is the time is 1 o'clock and I am going to eat something. So what the computational tool tells you, that person is hungry. That's it. But it doesn't tell you what the thing I want to eat. Right? If I want to eat chicken, it didn't tell you that madam wants to eat the chicken. But you can assess, I have hunger pangs.
Yeah.
Like that.
But even though still now we don't have an exact reference for that.
Okay, up to my knowledge, this is a basic principle.
Okay.
Some sensing materials are there. Those sensing materials sense our electrical and the chemical signals produced from the neurotransmitters, right from our neurons, and that get converted into computation.
I'm okay with electrical signals, but I'm not.
Neurotransmitters are there. Chemical signals, some acetylcholine, dopamine, like that.
I want to study with this chemical signals. I don't know about it, but I know electrical signals.
Thank you.
During the lunchtime, have a short meeting and have a short conversation, okay?
Thank you.
Yeah.
Sure.
Thank you,
But
sir.
thank you very much for nice explanation, yeah.
Thank you, sir.
I hope you understand the picture.
Yes, sir. Little bit I can understand what it.
Yeah. But if there is a problem means we don't know means what we need to eat, eh? Yeah.
Good afternoon, Ananda. Good afternoon, Ananda. How are you? So I just want to have some feedback, and if some changes are required, that I'm ready to help you. I'm very sorry I did not spend much time with you all. Earlier I used to be fully sit in the sessions. This is my third game program, but I'm not learning anything from Vijay. That is one bad thing. And so till today I understand that basics completed.
Yeah, basic about nanomaterial and basic about characterization. Next couple of days will be basic about sensing application. Yeah, sensors.
So what topics you will be covering? Chemical sensors?
Yeah, so tomorrow we will have at least means two topics. One is carbon nanotube quantum resistive sensor. The second is about graphene application sensor.
It means like what is the fundamental, like chemical, cyclic voltammetry?
I will no, it's not only cyclic voltammetry. We will have like First is about the standard, how to make these devices, and like, for example,
Okay, all experimental things were.
Yes, yes, most of them.
So after this, like, my plan is like how you came and when you are leaving, you should know basic fundamental things like cyclic and in our lab we have today you are. So we have a hydrogen sensing today we will be doing it actually. So the basic idea, like I not have a presentation kind of thing, just I will explain you sometime. Within 5 minutes I will explain the fundamentals. And then you can understand it and we will be using what is that? You can see.
No, I will ask a question, don't worry.
If you ask questions, it's very tough. I can't answer all the questions. So because I used to work in his lab for 1 month in when he is with Professor Mahendra Shankar, and he used to work in the company there. So I was there with him. So he used to ask very tough questions. So at that time in 2007, 16, 17, we planned this course, and it took almost 9 years to come to do actually. So basically, we have about Chandika will be explaining to you today is it's a we prepare nanomaterials, and then on the we have different types of IEDs with interdissociated electrodes. There are different types of interdissociated electrodes will be there. We quote these nanomaterials there, and the fundamentals here is when you are it's like a multimeter. You know, most of you know the multimeter. Basically, with the multimeter, what are the things we can measure? We can measure current, voltage, and resistance. Am I right? So, let us think this material is there, and we will be this voltammetric, calorimetric, and amperometric. There are different types of sensors are there. So basically, we will be doing chemoresistive, means we are measuring the resistance. And this resistance generally will be in the range of microohms, 10 to the power of -6 kind of things. So to measure that much sensitive resistivity, we need to have a setup called 4-probe setup. Rather multimeter, we have another meter called meter, where we will be using this meter there, and we will be sending the gas to that material. So what we are doing is we have a 4-probe setup, and then this nanomaterial on the interdissociated electrode is connected, and we will send the gas. And there are different ways to send the gas actually. Like ppms, we will be measuring in the ppms. We have another part. Actually, this is like almost 7 years before 8 years. Before 8 years, we started this 4-probe setup. Until it is working with the help of all the scholars, sincere and good scholars. So then we are modifying that instrument. First, we started with LPG sensing, and then we got 2 patents actually. With LPG sensing, what we did is different places, different activities we used to do. Basically, we were working on sensitivity of LPG and the temperature decrease. Like base temperature is required to excite these gases. Basically, oxidation reduction. When we are sending the gas, this material might be oxidized or reduction. NP, NPN, like negative, positive. You know, N material, N type of material, and P type of material. And this connection, this kind of things will be there. And if there are one table, I think I'll take some class for tomorrow or day after tomorrow. So there I will be explaining you all these fundamentals. So we will be basically measuring the resistive. That is what is the 4-probe resistive measurements, chemoresistive sensitivity. And from there we can do a lot of calculations, and from there it is not a one-day game. It's like all sensitivity, selectivity, a lot of other properties we need to understand, and from there we have to come up with these things. And then after LPG, we worked on carbon monoxide, nitrogen, and presently we are working on hydrogen. So hydrogen is like how much lithium you are doing? A very small we have to get, because this is a biomarker. We want to use as a biomarker for children and elderly people, those who can't speak, but they exhale a lot of hydrogen. that is the indication of indigestion and some stomach related issues, some gut issues kind of things could be understood in that as a taste test. So that is one way of doing it. Another setup what we have is cyclic voltammetry. We also do electrochemical workstation is there, and that we use for two purposes. One is for allergy studies, another is for glucose sensing. Especially, we started with non-enzymatic glucose sensing in the beginning with core shell nanoparticles. It is also once again oxidation and reduction, controlled oxidation and controlled reduction. It is all like playing with a very careful chemistry and understanding the materials kind of things and all of that. So that is another thing. Electrochemistry will be talking somewhere. Yeah, I will talk somewhere. We'll talk next. Yes. So it's a chemist, so it's the best person to talk about electrochemistry kind of thing. So basically, whatever we do and whatever my understanding of research is, it is like very fundamental thing. A small kid, how he starts to learn things, it is like that. Generally, there is very bad opinion about the research in the people, and somehow research quantity is reducing. And I used to have 6 to 7 people, all are funded in projects. Now only 3, 4 people with that only we are doing it. Earlier we used to have different projects we used to get, and students also. I can't say day by day things are changing. Nowadays I can't say students are not having fundamentals. We can't say that actually. So this is like this, like this, and you have to go ahead like this only. And here, the research, whatever you are doing, it is like, it should go like a flow. It should not be unnaturally you do something and you get some results, and it should be very natural way of doing research. That is what I feel. And and that is one thing. And I was told that food is not that much good, so I told him that please take care about the food. And no problem, you can give us any feedback you can give us. And then I told him very strongly. And someday people want biryani. Friday, tomorrow is best on Thursday or Friday. Some people might not. Chicken or mutton, whatever. I was told that the food is not that much good. So, Ali, you have to go to Sanka house. Don't eat anyway. Okay. Okay. So just 100 feet walking, there is Ali. We went yesterday. I took him to my gym also. Virendra did yesterday gym with me actually. So the things, if you have any questions also you can ask us. General things regarding the course, not or any other thing. How is the stay in the campus? Generally, my boss never scolded me when I'm doing my PhD in University of Hyderabad. I want to follow the same thing. So generally, they will be very free to discuss science and technology. Generally, some labs students won't discuss. They won't allow. My boss is not good. So generally, it will happen. Even when I'm studying in University of Hyderabad, also people won't allow other labs. But our lab is not like that. That I learned when my boss allowed everyone to lab. When we were PhD students, I used to feel why these people are coming. But after that, the networking is very good. If we allow everyone, like all of you can interact with Harish now, he became very close to you, Kailika and others. So whenever they come, you can like, so networking is very important in science and technology. And you can really interact, and I think you are accumulated with our department. It's a very small department, and but good quality work. Anything else?
We want to know about the working of the instruments, demonstration of the instruments, sampling.
One sample, what is that?
A characterization.
Characterization. What are the facilities? X-ray, No. Actually, there is a current issue was there for everyday fraction. Otherwise, it used to work very nicely. Some fluctuations are there. CFP is no problem. Before Friday comes. So, how many are you are staying in the guest house? Is it okay? If not, that's not key. We are trying to do that. Being a visitor, I'm trying my level best. Next, any workshop is there, we'll be doing that. And Sir is also in the campus. We kept him in
Yeah.
yes,
Yes, that's good. Yeah, that's not bad.
and I booked him for Rally Sir. In the meantime, Vice Chancellor advised he can hear so he can interact with them. So, so and among us, Sir is also a professor from RV. Sir is a professor of chemistry. And any other faculty? No. Ramchandra. We are all from that. Seven, six. All East Godavari. Yeah, those who are not from Andhra and Telangana, East Godavari is a rich district here. Sir Arthur Cotton, he developed all the bridges and barrages, and because of that, they are all very rich. So many of you are from Tamil Nadu? Which university? Savita, where is that? Chennai.
Central University of Tamil Nadu.
Oh, Central University of?
Tamil Nadu.
I have one, my Venkatesh from Physics Department.
Venkataraman.
Venkatesh is from
No, sir. No.
Physics.
Yeah, I'm from Physics Department.
Uh,
No, there is no sir in Venkatesh.
I forgot it.
There's,
You are the faculty?
sir,
Saravanan?
Ravindran sir, Ravindran, he's the head of the department. Then Shekhar sir, then Malai sir, and Nirbhay Behara, then Sampurna, and Kavita and Madhurima. Those are the five.
Only this faculty.
Yeah.
It is near to Kerala, no?
No, sir. This is Tiruvallur. It is near to Naraikal.
Oh, it's near to Kerala. Venkatesh Sharana?
Yeah, he's ex-faculty, sir. Yeah.
He, my friend.
Oh, okay.
He used to, he will work for PhD.
Yeah.
What are you working?
So I'm a recently graduate. I'm a recent graduate. Last year I graduated. I'm looking for the PhD opportunities. Sir, I'm from Madurai. I'm under Madurai Commerce University.
So from University of Madras, Chennai.
Oh, Balakumar.
Yes. Thanks.
Sir, we are from SSN College.
Oh, SSN.
Sri
Shivnata. Oh.
I'm from same institution, sir.
Oh, SSN College, you have a department in research.
Yes.
Sir, I am from Avinash University, Kanpur. Avinash University, Kanpur.
Where?
Coimbatore.
What is the university name?
Avinash University.
Private university.
Dean.
DV.
So same university, Avinash Nigam University, Kanpur.
Thank you.
So you're all PhD students?
MS.
Chemistry.
MS student.
MSc student. Fantastic. So is it useful?
So much than I expected.
SRM Institute of Science and Technology, Kalash University.
Seven.
Institute of SRM Institute.
Already group. What are you from biotechnology department?
Yes.
How many of you are? All are PhD.
No, sir, undergraduate.
How is this course for you? Like, are you comfortable with this thing? Are you learning something?
So it's actually good, but I mean, like comparing to others, we are undergraduates, right? So it's like we have to kind of.
You are Gen Zs, you are more better than us actually.
Yes.
Millennials, Gen Zs.
Yes, no, but I kind of it's like we are understanding the concepts, but for us, we are thinking that it would be more. I mean, if you guys like explain it in a very simplified way, it will be I mean, easy to understand for us. So it's little complex for us to
Yeah,
understand.
basically, ours is a nanotechnology department where we prepare different types of nanomaterials. General material, you need to understand comparison between normal material and general material, nanomaterial, and then how it is applicable. It's like what all research we are doing is very, very simple things only, but people complicate it. Like Raman invented an effect. What is Raman effect? So he is not a, basically first he is not a physicist, he is an accounts person. And when light is going through material, it is coming out with two will shifts. Actually signature will come. Till now people are working on it. So to do research, it is general knowledge and normal love towards the nature is required. And understanding simple things. And one boy came and told that apple is falling due to gravity. And before also apple is falling. Everyone knows that apple is falling, but someone will come and look at it in a different perspective. That is. So wish you all the best. And young group, we feel happy.
Actually, when we I mean, when
Sitting
service.
7 hours for you people is tough time.
Not like that. I when sir was explaining, sir was asking like, what are you guys discussing among yourselves? We were just discussing because any one of them knows like how the instruments work and everything. But we are like we were discussing this is the principle that's
We
kind
have
of
a
like
biotechnology department here.
okay.
One day I asked another department
Okay.
what all they are doing, how they are doing. You can interact with them.
Yeah, for sure. Sir.
Yeah,
I mean,
so ask them all this biotechnology people can visit the biotechnology department and what they are doing. I'll ask them to spend 1 or 2 hours. Scholars and faculty.
okay.
And just listen what they are trying to do. If
Yeah.
something is there, you can interact with them and it might be useful.
Yeah.
Nano, bio.
Yes, sir. Yeah. I mean, the session ends at 3:30, I guess. So can we interact? I mean, after that.
I'll ask them. I'll ask. Give me 1 day.
Okay.
However, it will be in Hyderabad.
Yeah, yeah.
I'll give it 1 day. You can plan.
Oh, okay, sure, sure, sure. Thank you, ma'am.
And sure. I'll try. From Hyderabad, no. Oh, your PhD
Electronics and
what made you to come here?
so I'm doing a metropolitan and
Actually, one student, Srikanth. Srikanth, one student used to be the Srikanth, his name, BTech second year. He started with me BTech second year, third year, and he published in BTech only 2-3 publications. And then he went to PM Research Fellow in Central University of Hyderabad. And now he's an Amrade. He went to France. In the middle of his PhD, he went to, I could see in the Instagram or somewhere there before section. So he's to France and he's doing some very good work, not France. So he's doing good work. So this kind of interest makes you, it's like you don't know, like, and if people may be earning after BTech immediately 1 lakh rupees and enjoying. If you like that, that's okay. And this is little different, and if you enjoy research, it will be very useful. But living life is very important. If you don't like something and you are doing that and wasting your time, and finally you don't know what you are doing, and everyone will live whatever you have happily, you can live basically. And how much you want to earn, how much money makes you happy or unhappy, you don't. If really money makes happy, people should not suicide. A lot of rich people will be suiciding, a lot of things. So, like, what exactly you want and how you want to live. It's interesting. I appreciate. BVI. Oh, faculty also. Oh, fantastic. Ram Kumar Nara. Okay. physics master Lakshmanarayana garu, I know one nice word. Fantastic. This college is very good college. Now and then I will take breakfast there after riding 100 kilometers cycling. That is around 55 kilometers from here. We go there and we take different cycling. So nice college. BBRI is very good college. So you are from Anna, Jaivel sir, Jaivel and Madam, two another madam will be there in the department, nanomaterials. They have sent. They have sent. Nine months which department? Oh, you are Coimbatore. You are from Coimbatore. I come to Coimbatore. Sadhguru Isha Foundation, I received visiting there. Nice to interact with you all. Thank you very much. So if anything is there, please give the feedback to them. They will give everything. Whatever you tell me, they will tell me. So I see that they stay a bit more comfortable and useful technically. And if you want one class, I want to take on abstract writing. So I did a course on manuscript writing for non-native speakers in US. So I will take some how to write an abstract because it's a big course actually. So I'll give you that book. You can read that book. It will be very useful for you. And some 30-40 minutes I'll try to take it. Because I'm registered, little administrative works will be there, so somehow it will be very tough task to interact. Thank you very much. I thank Vijendra for his support. He is so simple. So I'm not putting much concentration on him actually. So he's taking care of himself now and then I'm taking care. So thank you. I want to have lunch with you, but ACP and CIT some issue was there.
Friends, like, would you like to have this now or at the end of the evening session? You want to have this? Okay, let us do it at the department 334. We will hardly like 10 minutes, right? Before you wind up, we just give the best because it's already done. I think everyone is having.